Hello everyone, welcome back to the CSE Guy. Today we are diving into some fundamental concepts in artificial intelligence and search algorithms. We will cover intelligent agents, search strategies like breadth first search and depth first search, uniform cost search, the A-star search algorithm, heuristic functions, local search algorithms, handling non-deterministic actions, adversarial search, the minimax algorithm, alpha beta pruning, and the Monte Carlo tree search. So let's get started. First, let's explain the concept of an intelligent agent. An intelligent agent is an entity that perceives its environment through sensors and acts upon that environment through actuators. The goal of an intelligent agent is to maximize its performance based on a predefined set of criteria. Now, what are the characteristics of rational agents? First is autonomy. Rational agents operate independently, making decisions based on their own experience and knowledge rather than relying solely on external input. Second, goal oriented. They have specific goals they aim to achieve, which guide their actions. Third, perceptive. They can perceive their environment and gather information to make informed decisions. Fourth, adaptive. Rational agents can learn from their experiences and adapt their behavior accordingly. Fifth, utility maximization. They choose actions that maximize their expected utility, balancing between different possible outcomes. Now let's compare and contrast breadth first search and depth first search. Breadth first search explores all the nodes at the present depth level before moving on to the nodes at the next depth level. It uses a queue data structure. For example, if we have a tree structure, BFS will explore all nodes at level 1, then all nodes at level 2, and so on. Depth first search, on the other hand, explores as far down a branch as possible before backtracking. It uses a stack data structure. For instance, in the same tree structure, DFS will go deep into one branch until it reaches a leaf node, then backtrack to explore other branches. When we compare both of them, memory usage. BFS can consume a lot of memory as it stores all nodes at the current level, while DFS uses less memory since it only needs to store nodes along the current path. Second, completeness. BFS is complete. It will find a solution if one exists. DFS is not complete. It may get stuck in infinite branches. Third, optimality. BFS is optimal if all edges have the same cost, while DFS is not guaranteed to find the optimal solution. Now let's describe uniform cost search. Uniform cost search is an extension of BFS that takes into account the cost of reaching each node. It uses a priority queue to explore the least costly path first. Advantages: UCS is complete and optimal, meaning it will find the least cost path to the goal if one exists. It can handle varying edge costs effectively. Limitations: UCS can be memory intensive as it stores all nodes in the priority queue. It may be slower than other algorithms like A star in certain scenarios because it does not use heuristics to guide the search. Next, let's explain the A-star search algorithm. A-star search is a popular path-finding and graph traversal algorithm that combines the strengths of UCS and heuristic-based search. It uses a cost function f of n is equals to g of n plus h of n, where g of n is the cost to reach node n. H of n is the estimated cost from node n to the goal. For example, consider a grid where we want to find the shortest path from point A to point B. A star will evaluate nodes based on their total estimated cost, exploring the most promising paths first. A star is complete and optimal when the heuristic is admissible, meaning it never overestimates the true cost to reach the goal. Now let's discuss the importance of heuristic functions in A star search. Heuristic functions provide an estimate of the cost to reach the goal from a given node. They significantly impact the performance of A star search by guiding the algorithm towards the most promising paths. A well designed heuristic can drastically reduce the search space and improve efficiency. For example, in a grid based pathfinding scenario, using the Euclidean distance as a heuristic can help A star quickly identify the shortest path to the goal, while a poorly designed heuristic may lead to unnecessary exploration of less optimal paths. Next, let's explain local search algorithms. Local search algorithms are optimization techniques that explore the solution space by iteratively moving to neighboring solutions. They are particularly useful for solving problems where the search space is large and complex, such as the traveling sales problem or job scheduling. Applications of local search algorithms include hill climbing, simulated annealing, and genetic algorithms. In hill climbing, a simple local search that continuously moves toward the direction of increasing value until it reaches a peak. In simulated annealing, a probabilistic technique that allows for occasional moves towards solutions to escape local optima. Genetic algorithms. This use principles of natural selection to evolve solutions over generations. Now let's discuss strategies for handling non-deterministic actions in search problems. Non-deterministic actions can lead to multiple possible outcomes, making it challenging to predict the next state. Strategies to handle this include state space representation, representing all possible states and transitions in the search space. Second, probabilistic models, using models that like mock-off decision processes to account for uncertainty in actions and outcomes. Third, planning, developing plans that consider various possible outcomes and contingencies to ensure successful navigation through uncertain environments. Next, let's discuss adversarial search and the minimax algorithm. Adversarial search is used in scenarios where multiple agents compete against each other, such as in two-player games like chess or tic-tac-toe. The minimax algorithm is a decision-making algorithm used in this context to determine the optimal move for a player, assuming that the opponent is also playing optimally. The algorithm works by maximizing the player's minimum gain, the best worst case scenario, minimizing the opponent's maximum gain. The game tree is explored recursively, with each node representing a game state. The algorithm evaluates the utility of terminal states and propagates these values back up the tree to determine the best move. Now let's explain the alpha beta pruning technique. Alpha beta pruning is an optimization technique for the minimax algorithm that reduces the number of nodes evaluated in the search tree. It maintains two values, alpha and beta. Alpha, the best value that the maximizer currently can guarantee at that level or above. Beta, the best value that the maximizer currently can guarantee at that level or above. Minimizer can guarantee. When the algorithm finds a move that is worse than the previously examined moves, it can prune that branch, effectively skipping unnecessary evaluations. This significantly speeds up the search process while still guaranteeing the optimal move. Finally, let's provide a detailed explanation of the Monte Carlo tree search algorithm. Monte Carlo tree search is a heuristic search algorithm used for making decisions in complex environments, particularly in games. It builds a search tree incrementally and uses random sampling of the search space to estimate the value of different moves. The Monte Carlo tree search process consists of four main steps: selection, expansion, simulation, backpropagation. First, selection. Starting from the root, select child nodes until a leaf node is reached. Second, expansion. If the leaf node is not a terminal state, expand it by adding one or more child nodes. Third, simulation. Perform a random simulation from the new node to a terminal state to obtain a result. Fourth, backpropagation. Update the values of the nodes in the path from the new node back to the root based on the simulation result. Monte Carlo tree search is particularly effective in games with large state spaces, such as Go, where traditional search methods struggle. That wraps up our discussion on intelligent agents, search algorithms, and their applications. I hope you found this information helpful and insightful. If you enjoyed this video, please give it a thumbs up, subscribe to the CSE Guy for more content, and leave your questions or comments below. Thanks for watching and see you next time.